Okay. This is Durward King with Sanford Community College. The class is ELC 117, and we're on our second day, January 12th, 2021. And let's see. Yeah, let's start that over again there. Anyway, here I am. Started out with my video not on, but here we go. Okay, so. Okay, we'll go ahead and we're going to go ahead and roll through this. We pick up from where we left off, and they have a suggestion: work with one hand when possible. And what they mean by that, and most of the time that's not even practical. To be honest with you, in my opinion, it's not practical. That suggestion would be if you didn't have the electrical gloves, if you didn't have these, if you were barehanded, and you were exposed to something, energized, they're saying that if you work with one hand only, put one hand behind your back, you're less likely to get killed, because if you did touch something hot, the current would run through here, and instead of it running through your chest out the other hand to ground, it would run through your hand down to ground through your leg down one side of your body instead of through your chest. Still not good, but the best thing is to have these, and you just go ahead and work with both hands. That's just the normal way of doing it, because it ain't practical to do much at all with one hand. You think about that. I wouldn't even have put that in the book. If I had written the book, I would have just gone ahead and said, make sure you use these at a certain tender time. So, how you doing, Bismarck? Yeah, the only reason I'm doing the Zoom is because of one person's quarantine. And his family's got it. He ain't got it, but his parents and his sisters have it. So we've got Alex, Zachary. Zachary's not in here. I think he's coming by this one. Okay, Eric is here. Luke. Daniel Moore, gotcha. Taekwon's here. Cameron Norris, that's you. Yep, okay. Nathan Piercy is not in yet. Benjamin is here. John and Roger. So we're missing Brandon and Zachary and Nathan. Okay. If you see here, anyone working on equipment, especially those working with voltage greater than 50 volts, that number I mentioned yesterday, that's the number that OSHA says that when you get 50 and up in voltage, you need to have the glove on. That's kind of the number. But in my opinion, you could be working on heating and air equipment where you got 24-volt control voltage on heating and air systems. And to me, if you're working on something, I know most of them guys ain't gonna have gloves, but it was still wouldn't be a bad idea. If you're having to actually disconnect and connect things with power, if you're having to work hot, I would suggest having the gloves anyway, even below 50 volts. A avoiding alcohol and drugs. We all know that impairs whatever you do, whether it's driving, it's going to impair your judgment, it's going to make you sluggish. You're going to have delayed reactions, and your mind's going to drift. If you're even on some prescription medications, it's not good to be doing electrical work. So it's a warning. Now, the effects of electric current on your body. Now, when we go talking about that, we're going to look at different levels of current going through your body. What does it do to your body? What's the effect? And before we talk about current going through your body, for those of you that haven't had any electrical classes, I want to give you a handout, and let's define what is voltage and what is current and what is resistance. Let's make sure you understand what those three things are. So if you haven't had any electrical classes, raise your hand. Anybody else? If you want one of these, you can have it. I'll give it to you in electrical classes before. If you put that in your electrical, have so we can go back to okay. This will be a repeat for a lot of you, but because we normally do have first timers in these classes with no electrical, we don't have prerequisites, so you don't have to take intro to electricity before you take this. Years ago, when I was a student way back, you had to start in the fall. You couldn't start in spring. Couldn't start in the summer. You had to start in the fall. So you could. I think nursing may be that way. Maybe. But anyway, 3 basic measurements. This meter will do 3 basic measurements in electrical. And your first one is voltage. So when you go to voltage, you put it on V. And this particular setting on this meter will work for whether it's AC or DC. It's automatic selection, automatic detection. And it tells you whether you're in contact with AC or DC or not, automatically. Now, let's look at what does the word voltage mean? Voltage means electrical pressure. That's the best way to look at it. It's what pushes the current through the wire. It's like a pump. You know, a pump pushes water through a pipe. The pump gives the pressure, and the Duke Energy, their generator gives the push, it gives the voltage, it gets it to us, it gets the current to us. And those are the abbreviations for voltage: V, E, EMF. And it's similar to pressure in fluid power systems like hydraulics, pneumatics, air. It's similar to that, where we use pounds per square inch for pressure in fluid power. In electrical, we use voltage as the unit. That's what we use, okay? That makes sense? Okay. If you compare electrical quantities to mechanical things, you got a better concept of it. You can't see electricity. The only way you can tell what's going on with it is by using the meter. But the quantities, you want to know kind of what's it like in physical terms, you know. So that's why I'm showing you this, so you can have a better chance of you know, wrapping your head around these things. And really, voltage, when you measure voltage, the meter really tells you the difference in pressure between 2 points. Now, once you start using the meter, that'll start to make a little more sense. Normally, you take that black probe, that common, and put it on ground or neutral. You'll put that common probe most of the time on a 0 volt reference point in a circuit. And that red one's going to go to probe a signal that you're going to be tracing in most cases. So in some cases, you'll have these on 2 hot wires that are different. But for what we're doing in here in the beginning, you know, that comma is going to go on a 0 volt point for reference. And then the meter tells you how much voltage difference is between the red probe and the black one. That's what comes on the screen. It'll tell you if it's 120 volts or some other voltage.
I got a question.
So it's pressure. How much? Yeah.
So like the V and the E and the E, M, F, like you see that, like you already know, like that's for voltage.
It's voltage.
Okay.
The E is electromotive.
Okay.
For electromotive, like a locomotive, you know, a train is a locomotive, you know, with electricity, it's the electromotive force that a generator generates.
Okay.
So when you look at formulas like Ohm's law, they use E instead of V. Okay. You know, I don't know, since you haven't had any, whenever you in the fall, whenever you come for intro to electricity, you're going to get into using these formulas. And this is not to throw you a curveball right now, but as you see in there, the E is used, not the V. Everybody else, most people in here can pass this. If you want to know, you see anybody want to know one of these Ohm's law sheets? But the guy that came up with the formulas, George Simon Ohm, that came up with Ohm's law, he chose the E instead of the V when he did the formulas way back in 1800. V is for volts. Voltage drop, it is. Yeah, you can be looking at voltage in terms of voltage drop. Yeah, or you can be looking at it in terms, you know, voltage can be looked at in different ways. What is the voltage or what is the voltage drop? And what you're talking about was when in ELC 111, when we looked at if you had a 300-foot run of wire and you had, you know, 240 volts at the beginning, and you didn't have but say 235 at the other end, you had 5 volts of voltage drop. So that's something we get into in another class, calculating voltage drop and making sure that you've got enough voltage on the other end of a long run to run the equipment. So anyway, that's the definition of voltage. Current, on the other hand, is totally different. Current is the flow rate of electrical charge per second. So it's speed. It's how fast does that electrical charge flow per second in a wire. So it's not pressure, but it's flow rate. And current is measured in amps or amperes. So the unit that we use is officially the ampere, and that's the last name of a French physicist that defined current flow. His last name was Ampere. Voltage was named after another physicist, I believe it was, European. His last name was Voltaire. You can Google them, and it's these terms that we use were named after the people that defined it way back in the 1800s. You know, so for current, we use amps or amperes, and those are the abbreviations. If it's a whole amp, it's just A. You know, somebody A amps. And then if it's a fraction of an amp and down into thousandths of an amp, we use a little m and a big A, milliamp. Now milliamp, the reason why I'm showing you this is because milliamps is the range that we're looking at in the book. Is what does it do to your body when you get so many milliamps through your body? You know, and that's kind of why I'm having to define this. I is also used for current in Ohm's law formulas. If you notice on the Ohm's law, pie chart that I passed out, you use an I, not an A. So you look at the basic triangle at the bottom that has D, I, and R, that's volts, and then I will be current, R is resistance. So the I is used, and that's French for intensity. It's the intensity of the current flow, which means the speed. The speed of the current flow, the flow rate. It's like a river. If you got a river that's flowing slow, it's not intense. But if it's a rapid river, you know, the water's intense in speed, so it's for some reason they chose an I for the intensity of current flow as the abbreviation. You know, the faster it flows, the more intense it is. But we're not talking pressure, we're talking speed. Okay, there's a real distinction there. So for current, when you want to compare it in the mechanical world, and that's what I like to compare electrical to mechanical as much as I can. Current is comparable to what? Gallons per minute, which is a flow rate. And it's not pressure, but it's a flow rate. So if you turn on a water spigot and you have 2 gallons a minute flowing, that's your flow rate. That's your gallon per minute. And that's like saying so many amps in an electrical circuit. It's you know, gallons per minute and amps is comparable. Make sense? This is really important that you understand that right now in the beginning, because when you start measuring things and you're checking volts and then you're going to switch and check amps, there's a lot of people that don't know the difference. That honestly don't know the difference. And they might even interchange the words. Interchangeable and don't even know what they're doing, and they're saying it wrong, you know? Because they haven't gotten it down, broke it down to what we're talking about here is, what does it mean? Yeah.
So like, I don't know, like, you know, people have like speakers in their truck or something like that. Like,
Right.
Okay, you know how they have the wires. So like, do can have something to do with the wires blowing? Like you may get too much. It might like, I don't know how to say it, like.
You can blow
like
fuse
too much blowing, then you know how like the wire just blow. Right. Too much blowing.
Too many amps.
Yeah, or something like that. Right. Is that something that got to do with current or something like that?
It has everything to do with it.
Okay. That's what I
Fuses are rated in amps. Fuses are rated in amperes.
Okay.
You know, a 2 amp fuse, a 5, a 10 amp fuse. If you go above the rating of it for long enough, it's gonna burn the fuse in two.
Yeah, okay.
And the same thing with a circuit breaker. Circuit breakers are designed like fuses, like that's a 15 amp breaker. Well, that's like a fuse, and if you get above 15 amps for a long enough time, it's going to trip. But with this, you can reset it. With a fuse, you got to replace the fuse. But the amps is what makes these trip, the amps. These things are measuring flow rate. They're measuring flow rate. They're tripping on amps, not voltage. So that's what they're monitoring. They actually heat up. They heat up, or they're either heat sensitive or magnetic in the way they're designed. For fuses, when they get too many amps, they'll actually get hot and they'll actually burn in too. There's a fusible link inside that melts. It's a special mixture of metal in there that will burn in too. It's a link that's a certain metal mixed a certain way, an exact way to melt above a certain number of amps. And breakers can be thermal, and then some can be magnetic, the way that they sense the amps. So. Good question. Yeah. Okay. So everybody cool with those two? Now on the meter that you have in your hand, for you to check voltage, you're going to put it on V for volts, and you don't even have to know if it's AC or DC you're touching. You just contact the circuit, and it's going to tell you. The display will tell you by default AC, but if you go to a car battery and touch it, it's going to say DC. It'll switch for you. Now, there's other meters that you have to switch yourself. You know, this one has 2 settings for voltage. It has a voltage setting with a wave, and that's AC volts. Then it has a V with a straight line, that's DC. The AC voltage alternates. It comes in. That's what it comes in from the power company. DC is like batteries. The voltage stays nice and straight. It doesn't go in cycles. That's the simplest way to put it if you haven't had any electrical classes. batteries are DC, and then the power coming from the power company is AC. It goes in cycles. It goes up and down real fast. 60 times a second. But with this meter here, you've got to choose the right selection, or it's not going to read. If I put it on DC and I check a receptacle, it's not going to read it. You can falsely think that receptacle is dead, but it's not. So if you're not sure what voltage that you're looking at, whether it's AC or DC, the safest thing to do is start it out with AC and check it, and if it says 0, flip it over to DC and check it again, if you're not sure. You know, and then you've checked it on both possibilities, and if it says 0 on both of them, then you should be fine. You know what I'm saying? If you don't know, if you're in a control panel that might have DC and AC in there, and there's a lot of industrial panels that are that way to have both within them, and most of them do have both.
So is it a difference in between these two? Like, is this like,
yeah,
this probably like a positive, like, say it like that?
It is.
Okay.
For DC, it does matter. On the meters, you know, you want to put, if it's DC current, you want to put the red on the plus, you put the black on the minus.
Okay. So it's just like jumping cables. Like jumping cables?
Yes. It has polarity to it. It has a plus and a minus. It has polarity, what they call. And so the meter, if you hook them up backwards, then the meter will give you a minus sign on the display, and to tell you you've got them hooked up backwards. It'll still read, but it's just going to say minus 12 volts. You know, if I hook these up backwards on my battery, it'll still read 12, but it's just going to say minus 12, and then you'll know the flip your leads. So if you want to take a look at this one, it has the AC and the DC voltage. So you can pass that around. You got to think about it. The more elaborate a meter is, you got to think about it, because there's more features on it to choose from, and there's more chance of you making a wrong decision because you got it on the wrong set. You know. Okay. Then the third measurement here would be resistance, and resistance would be the property of anything in a circuit that opposes current flow. You know the word resistance from, like, if any of you go to the weight room and you know, work out, whenever you're lifting weights, you know, you got resistance there, right? Because you're pumping iron, right? And so the more you do that, kind of what happens to you, what's the result the more you do that? What comes out of your forehead?
Yeah.
You get sweat and you get heat, right? So resistance, when you're pumping iron like that, resistance makes you build up heat, right? Resistance also does that in an electric circuit. And a perfect example would be, does anybody know what this is? It's a heater element that goes in a hot water heater at your house. So if you have a standard hot water heater, you know, this goes in there to heat your water up. It's got a resistance element. And this thing, when you put voltage on it, it's got a certain amount of resistance. It doesn't stop the current, but it has got some opposition in there. There's a special mix of things in there that allow current flow, but it kind of pushes against it a little bit as it goes. And when it does that, you get what you're after. You get heat, so you can heat your water, and you can have hot water to wash your hands and to bathe in, right? So this is a perfect example of resistance, and you've got it on your burners on your stove. You've got it on your crock pots. Your coffee maker has heater elements. A lot of stuff you depend on every day has resistance to it, and resistance, in most cases, is a good thing, that we use it to get what we want. You know what I mean? Nobody wants cold food, right? So even when you open up the oven, if you look in the oven and look up top, you're going to see the coily, one of these, but a big version of a heater element. So resistance, it's in a lot of stuff that you depend on every day. So it opposes current flow, doesn't stop it, it just slows it down some. The more resistance there is in a circuit, what happens is it actually slows the current down some. So the relationship between the resistance and the current is this: if the voltage stays the same in a circuit and you increase the resistance, the current flow will decrease. So if the resistance goes up, the amps goes down. And then the opposite is true, that if the resistance goes down, what happens to the current? the current goes up. So if the resistance goes down, the amps goes up. They have a opposite relationship. Okay, they're not proportional. They're opposite. Now, if you have a circuit where the resistance stays the same, if the resistance stays the same in a circuit and you increase the voltage, then the current will go up. So current, voltage and current are directly proportional if the resistance stays the same. If you increase voltage in a circuit, the amps are going to go up if the resistance stays the same. That's another way to look at it, okay? So with that being said, just for a second, I'm going to put this on the screen for you to see, and we'll talk about what, actually, I just draw it over here. Yeah, let's just draw it over here. So you can see that. So the way the triangle works is like that. The way to understand what I just said in simple terms is this for you guys that it's your first go around. E is voltage, I is current, and then R is resistance. Okay. Now the way the relationship works is like this: is if you happen to know what the amps is and the resistance is in a circuit, if you know what it is, and you're solving for voltage, you cover up E, the one you're solving for, and you multiply these two. When they're side by side, you multiply, and it equals voltage. If you're solving for current in a circuit and you know the voltage and you know the resistance, if you know these two, and you're solving for this, you cover up current, and it equals I equals E divided by R. When they're over each other, you divide. Okay, so it's division. If you're wanting to solve for what the resistance is in a circuit, you cover up R, and what does it equal? E divided by I. So whatever you cover up that you're solving for in a problem, in an Ohm's law problem, you cover up the one you're solving for, and then the formula is there. If they're over each other, it's division, and if they're side by side, it's multiplication. So let's say for instance that you have voltage that stays the same in a circuit, but yet you increase the resistance. What happens to the current? By looking at the triangle, we want to understand it from the triangle standpoint. If I have 120 volts here, and then I increase the resistance, when I divide that and I increase the bottom number, what happens to this answer? Yeah, if I had, for instance, if I had 120 volts and I had 10 ohms. Okay, so when you divide that out, what is that? So how many amps would you have? 12. So what happens now if I double the resistance and I go to 20 ohms? What would the amps be?
6.
Yes. So you double the resistance, and the amps went from 12, cut it in half down to 6, right? So the amps was 12 amps, and now it's 6 amps because you doubled the resistance, and the current went down in half, right? So that's how you can see the relationship by looking at the triangle. Does that make sense? Now, at the same time, is if you go in, and I need to be moving this camera here. I'm forgetting to do that. Nobody's in right now, but they may be. Somebody will probably watch this after. I got to get back in the swing of remembering that this is for whoever may watch it later. Yeah. Okay. It takes a few extra minutes to do this, but it's what we call accommodating people that can't be here. And that's just part of, part of what we do. So now, what if you were at 10 ohms, and let's say, for instance, that the element begins to go bad and it begins to short out, that the resistance becomes less. Now, in most cases, one of these things, that the resistance gets higher and higher, and it starts going toward the open circuit, and you start losing heat, okay? But let's say, for instance, if it's short circuiting, you got low resistance. You went from 10 ohms and you went in half down to 5 ohms for some reason. It began getting less resistance within this. So in the beginning, you said you had what? You had 12 amps. So if your resistance goes in half, then what happens to the amps? How much is the amps now? Be how much? You can use a calculator. 24. So it actually doubled amps, didn't it? So if you cut the resistance in half, if the resistance goes down, the amps goes up, right? You see how that works? So that's the relationship that if you couldn't, they're oppositely, it's called inversely proportional. So current and resistance are inversely proportional. Amps and resistance inversely proportional. Now, what about amps and voltage? Are they inversely proportional? Let's say that we have a fixed amount of resistance. We have 10 ohms. And here you said we have 12 amps, right? Now we're going to say we got a fixed resistance, and we're not going to change this. We're going to actually increase voltage going to the element. So if I double the voltage, if it was rated for it, let's just say if it was rated for it. If I double this and go to say the 240 volt, and I keep the resistance the same, then what's the current now? 24 amps. So when you double the voltage, what happened to the current? It also doubled directly, didn't it? It's a direct relationship. So current and voltage are what you call directly proportional. Directly proportional. These two are directly proportional when this stays the same. These two are inversely proportional. Everything is hinging on the amps. When you compare amps to voltage or amps to resistance, that's what the comparisons are. They stem from is from a comparison to amps. What happens to the amps when you go up here? What happens to the amps when you go up here? You have a direct relationship and you have a inversely proportional there. So I know it's a repeat for most of you, but is that good for you? That it's your first time? Okay, good. That's good. This is important. It's very important.
Probably take a little bit more time, but
well,
I'm getting just a little.
You really, ideally, you start in the fall. Ideally, you take Introduction to Electricity, and we use Ohm's law formulas a lot. You spend a lot of time doing calculations, and you get real familiar with it. So in the fall, you will. In here, we don't do much of that at all. You're going to get really quickly to be able to wire circuits up and see something happen, with motor controls, So anyway, we use R in abbreviations, and we also use the horseshoe symbol. That's the Greek symbol omega, and that's what we use for ohms. So if you notice here over here, I put 10 and I put the little horseshoe symbol. We use the omega symbol for ohms. It's a Greek symbol that they picked. And ohms is It's the last name of George Simon Ohm. He's the guy that defined Ohm's law, the formulas. George Simon Ohm. You can look him up. He was a German physicist, and they said in the early days of when he mapped all this out and defined it, that everybody didn't really believe him in the beginning, but after a while they found that he was right. So he didn't get accepted in the beginning, but after a while everybody did accept it, and then the whole world adopted what he said. He was a German physicist, I'm pretty sure. So the Ampere guy was French, and the Voltaire, Voltaire might have been French too. I think he was. But all of them like physicists, and I think that's interesting. Resistance in fluid power could be a valve. If you have a valve, let's say you take a water valve and you go from wide open and you go halfway shut off. You slow, when you take the valve and go halfway shut off, halfway, then the flow, you get half the flow, right? So it's the resistance comes from a valve that's been throttled, partly shut. So when you shut that valve part of the way, you've throttled it back and you've introduced resistance, and so you slow down your gallon, you slow your flow rate down. When this increases, of course, this goes down. And that should everybody got you understand that good now? Okay. It's fundamental, and you need to know this up front now.
So like, what type of wire would we be learning, like just to like wire the factories or like anything?
In this class, it's going to be industrial stranded wire, for industrial.
Okay.
When you take residential, you're going to be using the flat roll mags, like some of that board behind right there. The house wire, your roll mags, okay. You put staples in, studs. So it comes in a different jacket.
Mm-hmm.
With that, you got 3 wires in a jacket, sometimes 4. In industrial, everything's got its own jacket, and you put it in conduit. So house wiring, you staple it to the studs. There's no conduit in most cases. So but you learn, if you stay with us, you'll learn all of it.
Okay.
Mm-hmm. Okay, so all of that was to try to get into a current of 2 to 3 milliamperes or milliamps, and let's define milliamps. Let's give you a prefix sheet here that talks about what does milli mean. So if you've never had the metric sheet on prefixes for electrical, if you haven't had it, raise your hand. If you want another one, I can give you one. I circled the ones that are commonly used in the electrical field. Would you like one? You still got one. You got one. Just give it the ones circled are used in the electrical field and also in computers and cell phone data. When you're looking at how much data you're using, so let's pull that up. So, need one. Okay. Yeah. Actually, I think the circled one. Let's pull it back up off of here. Yeah. By the way, when you go to Moodle, I put everything I'm handing you on paper. It's in there electronically too. The current voltage thing is there. You can download that to your phone. Then the Ohm's law, it's in there. Download PDF. I'm putting everything in PDFs on the Moodle. You can put them on your phone. Save it, The prefixes, you got to click that to get it open because it's in Word. Now, let me kind of define something here. I put notes on your handout that's not on here. We use most places in the world use the short scale for metric prefixes. Some areas of Europe use long scale, but we don't use that. I'm not sure what countries do, but long scale is a different. Instead of them saying billion like we say billion, or giga like gigabytes, gigabytes of data. Giga is G, and it's 10 to the 9, which would be. And here I am forgetting to move this thing around here too. Whoever's watching, sorry about that. Giga is an uppercase G, and it means 10 to the 9, or a billion in our words. In most of the world, it's a billion. A billion of something, like a billion bytes of data. A gigabyte would be a billion bytes, 1 and 9 zeros. 10 to the 9 would be 1 and 9 zeros. So that's a standard. That's what we call it, billion. And if you're into other world, other milliard, well, I never heard anybody call it that. You get into mega. So giga is common. Mega is also common. We used to talk about megabytes, but nobody talks megabytes now. Talk gigabytes, right? On data or on thumb drives or on hard drives, it's all gigabytes now. But mega is an uppercase M, and it's 10 to the 6 or a million, 6 zeros, 10 to the 6. Kilo would be 1,000 of something. Kilo is 10 to the 3rd. Now, kilo can be used in voltage, like kiloamps. If I have 1,000 amps, I can say I have a kiloamp or a kilovolt. If I have 1,000 volts, it's a kilovolt. 1 kV is 1,000 volts. So the power company talks like kilovolts because they're up super high out running power lines. So anything with a K after it, with a K and then some other unit behind it, kV, kilovolt, KA, kiloamps. Or if it's ohms, K in the horseshoe would be kiloohms, thousands of ohms, okay? And it means 1,000 of something. If it's volts or amps or ohms or kilograms in weight. If you weigh something in kilograms, grams, you can do weight that way, kilograms, 1,000 grams or something. So that makes sense. So those are used. The ones that are fractional, that are commonly used in the electrical field, would be milli. Let's stop on milli. Milli is a lowercase m versus the uppercase. So don't get confused between the two m's. Mega is an uppercase M and milli is lowercase. Everybody got that? It's your first time looking at these. Lowercase means milli. So here in our book, we're talking about milliamps, different milliamp levels that affect your body in a certain way. So lowercase m means milli, and it's the equivalent of 0.001, which means 1,000th of something. 1,000th of an inch, 1,000th of an amp. So if I put an M, I put a little m in front of amps, it's milliamps, which would mean 0.001 amps. It's 1,000th of an amp. Okay? Now, the way you can express that will be like this. 1 milliamp equals 0.001 amps. And the way you convert from amps to milliamps is like this. You take the decimal, you move the decimal over 3 places to the right, drop all the zeros, and you put the prefix in front of the A, and it lets you get rid of a lot of zeros. When you get in small quantities, they're using the prefixes to get rid of a lot of zeros. And when you look at it, you know that if you see a little m and a big A and some number there, the original position of the decimal would be 3 places to the left of where you see it. And then you would drop the prefix and it would be 0.001 amps or 1 milliamp. Everybody okay with that? So that's how you can flip between amps and milliamps, and to know where the decimal goes. Everybody okay with that? Okay. So that gets us to where you can look at the book and know what are we talking about between milliamps, because part of the paragraph says milliamps, and then they drop that and they go right back to standard amp, expressing it in amps versus milliamps. They do both in the same section of the book, and you just need to know how do you go from one to the other. It's just a matter of moving that decimal over 3 places if you're going into milliamps, or opposite if you're going back. There's other prefixes that are not used in this class that are used in electronics, or, well, actually in motor controls. Actually, there is, one of them is used in this class. Well, if you don't get the right button, it does what you tell it. Okay, other ones that are, another one that's used in motor controls would be micro. If you have a motor, any of you that work on hog farms, and you got your single phase motors that have a capacitor on them. If you got small motors that are single phase, and a lot of them have like a hump on the back, and you take the cover off, and there's a capacitor in it, kind of like a battery. It stores up charge, it gives the motor a kickstart when it begins. Capacitors are rated in microfarads. So micro would be 10 to the -6, or 0.5 zeros and a 1 of some measurement. A millionth of something is what it is. It's a millionth of something versus a million of something. It's a fractional part of a millionth of a whole of something. So capacitors, and it won't be but a couple of days where we'll take the cover off on one that you see, and how to test it. You can test the capacitors with this meter. It actually checks farads. It's reading in microfarads with this meter here. You can tell the battery. And those capacitors are used on heat and air motors and blowers at your house, and they're used on farms, stuff on fans. But the micro, this little U, it's a U with a tail on. I'm going to exaggerate it. If you see a U with a tail on it, it's a Greek symbol that means mu, M-U. Greek symbol for mu. And it means a millionth of something. So if you're going to have capacitors are measured in farads, and you say that capacitor is so many microfarads, like maybe 1,000 microfarads. And that's what will be stamped on that capacitor, and you can check it with a meter, and you can know is it bad or not. And that meter will tell you if it's close to that or not. Yeah. And I'm gonna spell the word out. Farad. Farad comes from Michael Faraday. He's one of the early pioneers, like George Simon on. Michael Faraday's one that kind of defined with capacitance. But a microfarad would be a millionth of one whole farad. Now I know you're into the big stereos like in car audio, right? Roger, are you into the big? No, somebody, I've had students that are, and I've heard some of them say that they got capacitors so big in those big, with the subwoofers and all, that they're in whole farads, that they're so big. I haven't seen any of them myself, but you know, some of these guys go to competitions on these big stereos that goes in these cars with the big woofers and stuff, and they have capacitors in them that charge up from the battery to stabilize voltage for that big stereo system. So when it's pumping, the capacitor keeps a steady charge for that stereo system that's drawn anyway. I'm just showing you that that unit is used. It's used for capacitors. You would use it in motor controls. It's the only thing you'll ever see it for in this class will be on a capacitor. So it is used. If you get into small electronics, which is not in this class, capacitors are measured in nanofarads and picofarads. So those other ones are for small, extremely small capacitors that are on computer boards, that are on small circuit boards, nano and picofarads. And it's really small capacitors that that function on computer boards and things, motherboards on computers, and in electronic devices. So but I circled all the ones that are commonly used in electrical and electronics, and you know that if you ever see those, that's what it means. That's what they mean. Okay.
So would you ever just see like one, like I guess if I'm doing something, would I ever just see like the label it got like what milli up there? I should know it's like
it's a thousandth of something.
Okay.
Now examples of milli would be, you can have a milliamp, you can have a millivolt, you can have a milligram. Amps, volts, grams, and weight, those are commonly used for milli. 1 milligram would be 1,000th of a gram of medicine. You know what I'm saying? So that it's used worldwide. The metric system is used. These prefixes are used worldwide for measurements, whether it be electrical measurements or weight, volume, things like that. It's used, even in distance. If you go to Mexico or Canada, distance or speed on the roads is not in miles per hour, it's in kilometers per hour. K. Kilo, kilometers, thousands of meters. So you see what I'm getting at? So the kilo is used in lots of things. Okay, the 1,000. So it's worth looking at this for a few minutes for you to have to broaden your scope a little bit on what we're looking at, because there's a lot there's a lot of stuff ahead in the different electrical classes that you take, and this applies to all of them. It applies to all of them, so you really do need it. Okay, let's see, click right on. I know this stuff, it takes time, but I mean, in my opinion, you need it. If we don't cover it, I feel like I'm cheating you. In here, they talk about a current. Let's see, let's back it up. They talk about in here, your body has less resistance on a hot day when sweating. So sweat, salty sweat, makes your body resistance go down. So what that does for you is, on a hot, sweaty day, if you're handling a power tool and that power tool has a short circuit in it, and you get a hold of, and the power line comes in contact with you on that drill, and you're sweating, there's more of a shock risk because your body resistance goes down. So what did you see over here on Ohm's law? If that R happens to be your body resistance, the number of ohms, your body has a number of ohms that changes through the day based on what you eat, based on whether you're sweating or not. Your chemistry changes the number of ohms that's in your body from hand to hand, almost continuously. So let's just say, for instance, that your body resistance is some number, and then you sweat and your body resistance goes down. So what can happen on the amps going through your body if the resistance of your body goes down? The current that can actually shove itself through you, it's easier for it to get through you. That's the whole point of all this stuff I've been saying, is that when body resistance goes down, the shock risk, it lets more amps get through. The river of current it speeds up, it goes through faster. So there's more risk on you getting really hurt bad or killed. Okay, so that's what they're getting at there. based on moisture, and also what you eat and what you drink too affects it. It's real complicated. So if you, and we're talking about the number of amps or milliamps that flow through your body, they don't measure this in terms of voltage. If you notice this, it's amps. So they don't tell you at a certain voltage what the effect is. They actually look at how many amps actually flowed through your body, how much current really got through you. So if you start at the bottom end, 0.002, which would be 2 milliamps, right? 2 to 3 milliamps, you get a tingle. You know, you kind of know something's going on. 9 milliamps, 9 to 10 milliamps would be a moderate sensation. 10 to 20 milliamps would be very painful. And we're talking, you know, 10,000 to 20,000 of an amp. It's way, way less than an amp. But it's painful. It is painful. Between 20 and 30 milliamps, you're unable to let it go. So then what happens in this range here, the current actually overrides your body's muscle control. Your body is actually bioelectric. So your brain, when you move, when I go to pick up that bottle, and I do that, my brain sent electrical impulses down to my muscles, and it made me do this like a robot and pick it up. So all that, I didn't have to think, that's all subconsciously. But my brain sent the electrical signal down there, a real small electrical signal to trigger my muscles, and that's what I did. Your body's bioelectric. And those signals are so small that when you get around this range, around 20 to 30 milliamps going through your body, it's actually stronger than your body's bioelectric system. And it actually wins the sort of the arm wrestling thing. There is the current wins out. The current that got in you through an external circuit, when it gets up in this level, it can actually take control and make your hands do this and grab a circuit, and you can't let go. So that's why it's so important to use these. It's important to use these because, you know, that's going to keep you from coming in contact. It's going to prevent the current from going through your body. These are electrically insulated, and so that's why you need them. And that's air compression. If you're ever in here and I leave that thing on like I did, there's a switch right behind here. You cut it off and it'll shut that off up there. We put a remote switch out there about 2 years ago. Okay, so anyway, right around that range there is where you can get a muscle contraction where you can't let go. Now, right in there is where I'll just go ahead and interject this part. We're getting ready to get to GFCI. Y'all know about the ground fault receptacles in your bathrooms and sinks with a test button to reset. These are set up the GFCI is designed to trip between 4 and 6 milliamps. That many amps, or you can say from 4 to 6 MA. The GFCI trips between 4 and 6 milliamps. If it basically, when on a GFCI, you know, you've got your hot terminal and your neutral terminal. If I plug a drill into this thing, the current goes from the hot terminal out to your drill, goes through the drill motor, comes back on the neutral. And so if you draw, say, 3 amps to that drill, then 3 amps should come back on the neutral, and the hot and the neutral current should be the same. So however many amps leaves and goes to that drill, if it's, say, 3 amps, it should be exactly 3 coming back to the neutral. If it's not 3 coming back, if it's less than 3, And if it's less by this amount or more, if there's this much missing when that current comes back, this trips. So the ground fault, what it functions on, it does the function on overcurrent like a breaker does. The circuit breaker is, if it's a 15 amp breaker, it trips if you get above 15 amps. That's not going to save your life. If you're down around the milliamps in here to where we're talking way less than an amp, this is worthless to save your life. Circuit breakers are to protect the wiring, the actual wiring, the circuit, not you. Because you would be long gone by the time that thing trips. The GFCI is to protect you. And all it doesn't sit there and look for 15 amps and then trip. It doesn't do that. It's looking for, it compares the amount of current that left the receptacle to that device and what come back on the neutral. And it compares them. If they're not equal, it trips. So it looks for missing current or leakage current that might have been going through you to ground, if that makes sense.
Does that work the same way on the ELC?
Well, no, the arc fault, what it does, AFCI looks for arcing. It senses if you have a loose connection. Let's say I've got a drill plugged into here, and then the cord is being cut or stepped on. And I have two wires in that drill cord that are arcing together, like a spark plug sizzling, arcing. If you get arcing going on in a power cord or in a device, a AFCI arc fault receptacle or breaker, it will trip if it thinks something's arcing. It senses arcing going on. It knows the characteristic of arcing, and it's exclusively looking for that. Well, if as far as arc fault, the arc fault kind, well, it depends. If you have an arc fault breaker and the arc fault breaker feeds a lot of receptacles, then if it picks up an arcing on one receptacle, it's going to kill the whole branch, the whole circuit coming off of that breaker. But if you are using arc fault receptacles and they're coming off of a plain breaker, well, that's not even legal to do that. You got to, I mean, the whole branch circuit has to be arc fault. You can still use these, but you still got to have arc fault breaker. It's a little catch-22 there. But let's say if you have arc fault receptacles, then it's supposed to be to where only the one that has the arcing trips and the rest of them are not supposed to. But you still could end up with the main one in the panel. It could. So that's my understanding on code is you got to have an arc fault breaker at the beginning anyway for the whole branch circuit, even though you may have arc fault receptacles. That's my understanding of it. But anyway, the GFCI trips in this range before you can have this condition of a muscle contraction where you can't let go. So that's the whole reason why what we're hitting in this chapter is that you need to be, you need to be using the GFCIs, and if you don't have it in wherever you're working at, just use the pigtail. They got the short pigtails. You can get it at Lowe's. It's a little box with a short cord on there, and you can plug it into any plain receptacle, and it gives you GFCI portably, and you'll have it no matter where you go for power tools. So that's the reason behind that. And you get up higher, 30 milliamps, 40 milliamps. You can have muscles can paralyze, breathing difficulty, 40 milliamps, 60 milliamps. It can be hard to breathe. 60 to 100 milliamps, extremely difficult to breathe, and you're still not even at a whole amp yet. You're still at a fraction of an amp. Okay, and then 60 milliamps to 100 milliamps, extreme breathing difficulty, and around 100 milliamps to 200 milliamps, death. So that's where you would be gone. Causes fibrillation of the heart, which means the heart quivers and it doesn't pump. It's just shaking, oscillating, but it's not pumping. It's lost its pumping action. And so that kind of current there throws your system into a tailspin. So this is not to scare you, but it's to say you'll enjoy doing the stuff. You'll enjoy wiring it, and when you see it run the motor and you see the controls and stuff, you'll have a sense of satisfaction seeing that. So just realize that you got some life for everybody. Okay, you got that. You got your arc flash. You got your arc rated clothing. And so it's up to you to remember. Sometimes I may forget a little something here and there. I'm a human being. Okay, I ain't perfect. I'm gonna tell you. So it's gonna be up to you and me both, us, to look out for you. You know what I mean? So remember this stuff here. Okay. Any questions? You can also have severe burns that happen inside the body. The more current there is, it can actually burn you on the inside before you even see it on the outside. Now, it's kind of like, it's not like a microwave, but a microwave can heats up internally, inside out. Electric current's kind of that way. I'm not going to get into OSHA. OSHA is something that y'all probably heard about a lot in other classes. Has anybody never heard of OSHA? That's your Department of Labor, and they enforce safety in the workplace. They can come into where you are and they can inspect. They got a right to come in and check out your place, get you fines if things are not safe. So they have a right to walk in. They're again part of the Department of Labor. And I've seen it happen. I've seen them knock on the door in the plant, and they got authority to come in. So, hazardous material.
I'm not asking to shut the place down.
Yeah. Yeah. Right. Right. Yeah. We had one manager that wouldn't let them in. Boy, he messed up there. He messed up. And they said, "Okay, well, we'll be right back." So they went and got some paper, warned something under downtown, and come back. They socked it to us as far as they nitpicked every little thing they could find, so he should have let them in first time, but not good. Not good. Hazardous materials, you have something called a material safety data sheet, and that's whether you're dealing with PVC glue, anything you're dealing with in maintenance that's got a hazard to it. There'll be a safety data sheet, and wherever you work, they're supposed to have a notebook with all the data sheets in there. You can read them anytime you want to if you're dealing with chemicals. I used to work with waste treatment. I had to mix chemicals manually in water treatment system, and so you had to have certain PPE on. You get certain kind of gloves and gown, and when you're pouring acid and stuff, and whatever you're working around, be aware of the hazards of it. And wear the proper PPE no matter what it is. Even though I was an electrical guy, I got pulled into doing waste treatment and running it sometimes when the guy was not in there. And I found myself mixing, like acid and caustic soda and different things. And you got to have all your right stuff on. Know where your eye wash station is. If there's an eye wash station right here, even though we're not doing anything in here. You want to know what that is? If you're doing something, get something in your eye, you go and get that paddle, and then things will fly up, put your head up there, and it'll win your eyes out. I saw a guy one day mixing chemicals in West Street where I worked, and his glasses were on top of his head. And he was sitting there pouring caustic soda mixing a tank for water treatment. One drop of that stuff in his eye, and it was like a fire. He started hollering. He couldn't even get to the eye. So another guy in there got him over there and took him over there, and he couldn't even get through the cell. You need one. He should have had on these plus, you know, a chemical resistant face shield. He should have had all that stuff on, you know. So, bad thing was when they took him to the doctor, they did a drug test on him. He never come back. Bad way to go. Bad way to go, man. Bad way to go. Not good. So anyway, kind of, you need to be asking.
I was just commenting on what you said.
Yeah, that was for real. It was for real. But anyway, be aware of the hazards of whatever you're dealing with. Your employer's supposed to keep you in the know about all that stuff. Next part is about trenches. There's a possibility if you work with on a farm, doing farm work, running a conduit, you may be dealing with trenches, doing electrical work. You can be reading this stuff on your own. You know, don't walk close to trenches. It can loosen, you can fall in them. Barricades. If you're working in confined spaces, they're going to train you wherever you work. If you work at motor ball, they have training on confined spaces. To where, you know, one guy goes in the tank to do some work, and there's another guy that can pull you out with a rope, a lanyard. If something goes wrong, he don't go in, but he can pull you out, things like that. And they got all that stuff set up. Not likely, that just depends on where you work. If you're working, I guess, on feed mills or something on farms, you could be in like this confined spaces. And in some plants, they've got tanks and stuff that you can go in that are confined spaces. So as an electrical guy, you could end up somewhere like that, working in, you know, tanks. So for instance, lockout, tag out. Again, there's I've got a PowerPoint that I've got in Moodle that, you know, you can go ahead and read it, and it gives you the 6 steps. And there's a quiz after that, a worksheet on lockout, tag out. Just about 20 questions. Your protective clothing, we've looked at that. Head protection. Some cases they got hard hats. I got one of these with a hard hat on out there. In motor ball, you got to have one hard hat with the arc flash. So it's bulky, but that's what they require. Eye protection is here and everywhere you go. Eye protection is a must. Hearing protection, I would recommend it. Earplugs are a hassle, but I got ringing in my ears because I went a bunch of years and never wore it. And I got a little ringing in the background, little like that going on, because I was running punch presses and hydraulic pumps for, you know, 15, 16 years before I started wearing earplugs. You know, I didn't start wearing them until each year the hearing test, when they come out of the truck, you go in there and you listen and you hit these little buttons. I started having hearing loss over here, and some, you know, it was, and then I said, I better start wearing earplugs. But you're talking 15, 16 years of no earplugs. And you develop a ring, and they can't fix it. They can't reverse that. So, you know, they're a hassle. You got to roll them up. You got to clean, hands got to be clean out. They're a hassle, but man, you know, use them. And I hope you don't get no ringing in your ears, you know, because this, the fire retardant clothing, you know, we've looked at here. If you're working, say, in Smithfield or Motorball, your shirts are treated, your pants are treated. They actually provide you with your clothes that are already treated. They give you a jacket that's got that company right there. They give you the jackets, and everything you got fits with like it. It's flame resistant, and then you got to take the clothes. They got to send them to a cleaner that's got the right stuff to wash them in, so it doesn't lose the treating in it. So you got to have it washed by a special chemical and cleaner. Gloves where necessary. Gloves can be a bad thing, like on a grinder out there. Pedestal grinder, I wouldn't use the gloves out there, you know, but they get hung. I wouldn't use them on a drill press. But if you're grinding, it all depends on what you're doing, you know, if it's required. Safety harness, you be reading all in there about, you know, how high is it that you, before you have to have a safety harness on, things like that. Scaffolds and ladders, be reading all that. I don't need to discuss all that stuff. The angle for your ladders, it's going to be about a fourth of the height of the ladder. Will give you the ideal angle. So it's about a fourth of that height. You know, you want to use fiberglass ladders, not metal, for electrical. Fiberglass. And then you could be reading on through here about the different classes of fires. This gets into the GFCI that we've already discussed. I'm going to stop it. It's 1:55. We got another class starting. I'm stopping right now. You can go ahead. You know, there's a worksheet you can do, and then there's also one on lockout tag out. Those will be due Thursday. We'll get into chapter 1 on how to read electrical schematics on tomorrow, and we'll get you to a point to where Thursday we'll let you go out here and actually start to wire some circuits up Thursday. Okay. It'll take tomorrow to get you familiar with how to read a diagram, enough basic one to how to know how to begin to wire push button and a motor starter and fuses and stuff. So we'll.
See you later.
Yes, sir. We'll see you later. And thanks for coming. I'll take that. Have a good one. Okay, we're into the session. I know I've been moving around a lot. I hope whoever's watching this was able to catch something out of it. I'm not moving the camera as much as I need to be, so sorry about that. But anyway, ask me if you have any questions about what we covered. Go ahead and try to do your worksheets in Moodle, the safety worksheet, and also the lockout tag out. There's a PowerPoint you can read. We'll cover some of that tomorrow, but you can go ahead and be doing those on your own. They're all due Thursday.